Hi guys, welcome to another video. So I'm Charlie, this is Vamos Gaming Systems. Can liquid metal be applied directly to copper heat sinks? So that's a question that has popped up in my mind, and also because of comments. So I have previously done videos such as deep cleaning as well as repasting for GPUs with liquid metal, and there was two videos that with two comments that caught my attention. One is my 6900 Sapphire Nitro Plus 6900 XT repaste video where I did liquid metal, and the heatsink was actually copper. So there was comments saying that direct application of liquid metal to copper can lead to corrosion, potentially affecting thermal performance. So that's valid. Then the other one is my video for a Gigabyte 2070 Super WindForce. For that is also a copper heatsink as well, I believe. Yep. Has copper cold plates, and then it says liquid metal must not be used in direct contact with copper, otherwise oxidation process will occur. Can only be used in nickel plated radiators. Okay, so pretty valid concern. So I wanted to test it out. So for what I have here is let me see, bring up the video that I have. I have a 3060 Ti. Let me mute this video. So I have a 3060 Ti that has gone through liquid metal application for a long time. So it has almost been a year since I last applied liquid metal to it. And this is a 3060, it's an Asus 3060 Ti, I believe a mini version. What's the version for this? Asus 3060 Ti. Dual OC, dual, wait. Dual mini. See, I think it's this one. Yeah, so it's this one. The Asus Dual 3060 Ti V2 Mini OC edition. So it's a pretty small card, two-fan design. It's good for small form factor builds, but because of the small fans and the small heatsink, it doesn't cool the chip very well. So in my case, let me try and bring up my video again. Yep. So to cool it a little bit better, I actually applied liquid metal to it. And it's been, I mentioned it's been a while, about 9 months to a year. I'm not exactly when. So you can see here when I disassemble it. So maybe speed up the video a bit. You can see that it's pretty dried up. So if I use Epic Pen, okay, play a little bit more. Yep. So as you can see, I bring it to, yeah, you can see that this is the copper cold plate. So whatever is on the copper cold plate has completely dried up, right? So it's like it became something like dried toothpaste. And if you're looking on the GPU die, as you can see my fingers go on it, and there's no liquid at all. And then for the GPU die, it's also completely dried up as well. So it looks like dried toothpaste. So this is the effect that the commenters has been so-called warning about, saying that liquid metal can actually react with copper, and it does. You can see that it actually reacts like with copper, and it creates sort of like a oxide film. So this actually dries up the liquid metal over time because yeah, technically liquid metal, as it participates in the oxide chemical reaction, it will be used up. So the liquid metal gets used up and it becomes this dried up paste. So I don't have a video for testing for the benchmark of this particular video card, but all I can tell you is that it definitely overheats. So when I plug it into the system and I immediately run a benchmark, the temperatures immediately spike. Hotspot temps immediately spike to like 105, which is the maximum it can go before thermal throttling. And yeah, I couldn't complete a benchmark, I think, because it was just running too hot. So in order to prevent the death of my GPU chip, I actually stopped the benchmark. But it was definitely overheating, and this is what they are warning about. So my issue is that, can I repaste with liquid metal and can it still work as normal? So in this instance here, I believe I clean the GPU die. I didn't really clean the copper cold plate, so I actually left the copper, like the liquid metal oxide layer, the metal oxide layer on the copper cold plate. Oh, in this case, I didn't even clean the GPU die. So I just reapplied. So can we just directly reapply liquid metal? And can it just work as normal after repasting it with liquid metal? Yep. So here, I'll just fast forward the sections. So just make sure that, yes, you have an even spread of liquid metal. And then same, I apply a small dash of liquid metal onto the copper cold plate with the oxide layer. You can see it's a small dot. And then same, we spread it out. So the texture of this copper oxide layer is kind of rough. It is like, imagine if your metal has rusted. So it's not as rough as metal oxide rust, as iron oxide rust, but it is still a little bit on the rougher side. So the surface is a little bit rough. It's no longer as smooth as original cold plate. So definitely that, I think, impacted the temperatures a lot, because we no longer have good contact pressure between the cold plate and the GPU die. Okay, so apply liquid metal on it, spread it out, then reassemble it. Yep, then this one we can skip, and then we go into benchmarks. So in terms of benchmarks, I think this is reapplied metal benchmark after the first one. Okay, so benchmark temps, this has been running for about 6 minutes. So we are able to complete the Unigine Heaven benchmark, and the temps are decent. So you can see that hotspot temps are here, about 87.7, and the average GPU die temps are about 76.2. So it's no longer overheating. It doesn't hit the 105. But I was thinking, well, can we get better temps than this? I cannot remember the original temps after I initially applied liquid metal to it, but I kind of remember, I don't know whether is it cooler than this or not, but because this GPU does run hot because of the smaller fan as well as smaller heatsink, so that is what it is. So I thought that maybe if I apply liquid metal again on a second time, it would do better. So, and then I reapply liquid metal for the second time. And this is my second application of liquid metal. You can see that it's a little bit thicker this time. And I apply, a thicker amount of liquid metal. Actually, this one I applied a little bit too much on the cold plate. So I'm actually using the cotton swab to try and drain some of it by transferring it onto a piece of toilet paper. So you can see here, I keep dabbing using the cotton bud, keep dabbing away the excess. And eventually, I think I reach a level which I'm somewhat happy, which is somewhat like this. Yep. And then I reassemble it and we test it again. So this is the benchmark after the second application. As you can see, the benchmark has been running for about 13. Oh, ambient temps is about 20. I think ambient temps is 27 in my room. 27 degrees Celsius. And if we pause and look at the temps, yep. So hotspot temps, still about the same, 87. And then average GPU temps still about the same, about 76. So fan speed still about the same as well. So even though I applied more liquid metal to it, it doesn't really improve the temps anymore. This is the consistent temps, but it is functional. Like after if you initially apply liquid metal to the copper heatsink, and after maybe like half a year to a year, you find that the temps degrade because it has formed a copper oxide layer. If you apply another layer of liquid metal to it, the thermal conductivity will still be around the same. You can still conduct heat pretty well. It can still work with a second application of liquid metal. So if I were to compare after, this is first application and this is the second application. So let's compare the temps. Okay, so if we can do a side by side. So, well, scores are slightly higher after the second application. Like benchmark score of 3,501 and 3,533, but this can be just due to margin of error. One average FPS difference can also be margin of error. because in the second application, the max FPS is slightly higher. Can be margin of error, can be due to lower ambient temps. Then you can see that actually the first application, the hotspot is actually exactly the same. You can see that the max hotspot on the first application is 88.3. Second one also 88.3. Okay. Maybe let me bring it up a bit here so that. Oh, okay. So it is more level. So maximum hotspot, same. Maximum GPU die 7624, exactly the same as well. Well, the average obviously can fluctuate due to the time that the result was taken, but you can see that actually hotspot temps and like the current GPU average temps are about the same. Fan speed 2006 on the first application, 2006 on the second application. So even though I applied more liquid metal on the second application, it didn't really improve the thermal conductivity. So basically, if you were to reapply liquid metal again on a copper heatsink that's been so-called contaminated or degraded with liquid metal, you can just apply another thin layer of liquid metal and it will work just as well. Okay, so that's it. So this to address the concern that yes, if you do apply liquid metal to copper heat sinks or copper or heat sinks with a copper cold plate, yes, there will be corrosion and forming of an oxide layer on the copper over time, as you can see in my earlier video, earlier part. But eventually, if you reapply a second layer of liquid metal onto it, it will conduct heat well again, so it will work again. How long will this second application last? I think only time will tell. So probably gonna keep the GPU for maybe another like 9 months to 1 year, and then we'll see if it dries up again after that 9 months to a year. But in my experience so far with liquid metal, I think even on nickel cold plates it does dry up as well. So yeah, liquid metal does eventually do dry out. Okay, so that's it for this video. So this kind of, yeah, can we apply liquid metal onto copper heat sinks or copper cold plate? Yes, but with a caveat that it will form a copper oxide layer and you really need to reapply another layer of liquid metal after some time, probably a few months. Okay, and we will see you guys in the next video.